this figure try to explain. Okay, the first one on mathematics. Basically, this one is equivalent to this one. Okay, so this one is equivalent to this one.
In the moment, right?
In terms of moment. In terms of moment. So that means they're existing. So say given vertical loading like this, they should exist. E. What is E? E is a distance measured from the vertical side to wherever the location of the V. So that means this one will be balanced. So that means is this. If we would have the cross section like this, rather than applying the V to that direction, but on the other side, if we have the V applied to a center, we call let me call the O. So if V is applying to these directions, then under these situations, this beam will be directly bent down, and then we won't have twisting.
Yeah, because it won't be subjected
because
to
that's this kind of reaction force. Okay, so in this case, we define this one. The distance here would depend on either whether I think this one is measured from the middle line. This one is called the E. E is called the distance from the shear center to the cross section. Okay, so basically O is we call the shear center. So basically here by doing so, we introduce the concept of the shear center is such that if we will be able to apply the transverse or to direct the application of the transverse loading through pointing to the shear center, then we will guarantee the cross section won't be twisted. So in terms of application, if you doesn't want your design to be twisted, then you better to try to put your kind of design into such that have the V directed to the shear center. In that case, you have to calculate where is the location of your shear center as the first step, and then you direct all the things in there. So the whole cross section, in this section, basically the first step exercise is on how to calculate the number of E, and this E basically is through this formula. We have to first to calculate the total force on the top or bottom, and this portion basically is perpendicular to where the V is applied. So you calculate this force. That force is the area integral of the shear stress. And then once you have that one, you simply take out the dimensions and put into this formula.
You're essentially you get that formula because of the moment, though, right?
Because of the moment.
Yeah.
Yes. Are we good?
But one causes the continuous twisting, and the other one doesn't.
Yes. Okay. So from here, the concept is pretty straightforward, and you can see right now we want to calculate this one. V is a given one, E is a certain number we're looking for, H is a dimension. So the majority of the calculation is on determining the value of F. What is F? F is this number. This number area, what is area, is pretty much is on the top one. Okay, the majority of the calculation of rigors will be on this part.
But it's not always that shape.
No,
so
yeah.
It
depends on the shape. Okay, so that's the concept. And for this case, probably we can see how to calculate this one. Okay, so this is the concept here. So once we have the loading applied to a certain way, for example, you can put a rigid plate, stick onto the end, then have the loading to apply to that point. You can do it in this way. Okay. So in that situation, then we can guarantee then the bending will be directly bent down. There's no twisting. Otherwise, if we would have a twisting, then we have other problems here. Yeah, look at this one. If we have the twisting, so the distribution of the shear stress here would be due to VQ over IT plus the shear stress due to twisting. And that twisting will go back to our original, the previous two chapters, the twisting of the thin walls. Okay, we will see the return an example here. So now our first step is to see. So probably we can calculate the E, okay, for this case.